Let's take a look at this problem. We have a parallel RLC circuit where we're given initial conditions for the voltage across the capacitor, which is the only voltage in the circuit, and the current upward through the inductor. And we want to find an expression for this voltage, the only voltage in the circuit, as it changes with time. So to analyze this circuit, if we were just had an RL circuit or an RC circuit, the first thing we would do is find the time constants. But since we have an RLC circuit, what we want to find is alpha, the damping ratio, and omega naught, the resonant frequency. So our alpha for a parallel RLC circuit is 1 divided by 2 times the resistance times the capacitance, or 1 over 2 RC. When we plug in our numbers, we end up with 3.5 per second. So that's like a frequency per second. For omega naught, that's always 1 over the square root of LC, and that's the square root of 6 per second. And this is actually a radian frequency, so we would call it radian per second. But what we want to do now is take a look at both alpha and omega naught and see how they relate to each other. And we see that the square root of 6, that's less than 3, so omega naught is less than alpha, or alpha is greater than omega naught. So that means we have more damping. Our damping ratio is greater than our resonant frequency. So we have an overdamped circuit. For an overdamped circuit, alpha is greater than omega naught, and our voltage response is going to be some constant A times e to the S1 of t plus some other constant A2 e to the S2 of t. So what we need to do now is find this S1 and S2, which are both also frequencies because we multiply them by time. So using our formulas for that, and using the formulas that include our damping ratio and our resonant frequency, we get that S1 is negative alpha plus the square root of alpha squared minus omega naught squared, and S2 is also negative alpha but minus alpha squared minus omega naught squared. So when we plug in for that, we get that our S1 is negative 1 per second, and S2 is negative 6 per second. So these are negative frequencies, which doesn't necessarily make sense. However, if we look at the time constant, then our tau1, 1 over S1, is going to be 1 over negative 1, or negative 1 second. So it's really equal to, we look at the absolute value of that, so our tau1 is 1 second, and our tau2, 1 over, we'll do the magnitude of S2, that's 1/6 second. So we see that the time it takes for this, our exponentially damped function raised to S2 to die out is 6 times faster than it is for, we have a time constant that's 1/6 of tau1. So that's important to recognize. So, but we can then plug that into our response and we get a A1 e to the negative 1t plus A2 e to the negative 6t. So we've evaluated, this is like evaluating tau. So this is what we have had to do to evaluate tau compared to an RL or an RC circuit. Now we have to find these coefficients to each of these exponentially damped terms, and we do that by looking at the initial conditions. So solving for A1 and A2, one thing we could do, if we had a value for the voltage at 2 instants in time, we could solve for A1 and A2. But what we have is the initial current through the inductor and the initial voltage across the capacitor. So with these two initial conditions, V of 0 is equal to 0 and I of 0 is equal to 10 amps, we can plug those in. We can plug in directly, so at time 0, we know the voltage, so we know one time, and that would just be e to the 0, which would give us a 1. So we'd have A1 plus A2 e to the 0, which would give us a 1. So A1 plus A2 is equal to whatever the voltage is at t is equal to 0. In this case, it's equal to 0. So that's easy enough to do. That gives us one equation. We still need another equation because we have two unknowns. So we can apply that voltage directly to our voltage formula. We can apply our voltage instance and to our voltage formula. How do we apply then the current? The current we're going to have to relate to, we can do a KCL. So if we did a KCL here, we have the current flowing into our V node, and then we have current flowing out, IC. Well, IC is C dV dt. We have a voltage here. And IR, even though it's shown flowing upward, the downward current is going to be V over R. So we could use a KCL, and that KCL equation would all be in terms of the voltage. And we evaluate it all at time t is equal to 0. So we just need our equation for IC, CdV dt, equation for IR, V over R. So, but because it's the opposite direction, it's active sign convention, we do negative V over R. But note this dV dt, we only have to evaluate that at t is equal to 0. So our dV dt, the derivative of this voltage with respect to time is equal to our negative S1, which S1 is equal to 1, so it's actually equal to S1. S1 is equal to negative 1, so it's equal to our S1 A1 plus S2 A2, don't have the 1 there. We just need to evaluate that, though, at t is equal to 0. And so when I do A1 S1, let me just correct that one more time. We also have that's S1 A1 e to the S1t plus S2 A2 e to the S2t. And when we evaluate it at t is equal to 0, that goes to 0, that goes to 0. So this whole term goes to 1, and then it's just equal to our S1 A1 plus S2 A2. So that's what we want to do here for our dV dt at t is equal to 0. We use our voltage function that has the arbitrary constants and the frequencies in there. So when we evaluate this dV dt, evaluated at t is equal to 0, we get C S1 A1 e to the S1 0. Well, in this case, our S1 is negative 1. C S2 A2 e to the S2 0. In this case, our S2 is equal to negative 6, and there's our second equation there. So when we plug in then for S1 and S2 and C, we end up with our two equations, negative A1 minus 6A2, 10 divided by 1 over 42, that gives us 420. So if we take these two equations together, we know that A1 is equal to negative A2, we get 5A2 is equal to 420, and A1 and A2. A2 is negative 84, and A1 is positive 84. Now these are voltages, so they have the unit of volt here. So we can solve then these two equations and two unknowns in that manner. When we go and look at this, we graph this, what we want to know is how can we graph it? Well, the voltage itself is going to be our 84 e to the negative t, that's this here in black, minus 84 e to the negative 6t. So we're subtracting these two voltage waveforms in black. What we're going to end up with is this voltage waveform in blue. So we know they both start at 0 and end at 0. And that's because our initial voltage was 0, and at t is equal to infinity, their function goes to 0. So what we might want to find is what is the maximum. So how can we determine where that maximum occurs? Well, we can use our calculus. We can take the derivative of our voltage function, set it equal to 0, find out the time that that happens, we can call that time Tm, and then plug that time back into our voltage equation. So we set our derivative of our voltage function equal to 0. The derivative of our voltage function then is 84 times negative e to the negative t minus negative 6. So we get plus e to the negative 6. And we'll call this variable now Tm. We want to solve for Tm. So that means this term here must be equal to 0. Well, we didn't take the derivative yet. So this term here must be equal to 0. We get e to the negative Tm is equal to e to the 6 Tm, because this will give us a negative 6. And so when we divide by e to the negative 6 Tm, we get e to the 5 Tm on the left is equal to 6. We can take the natural log of both sides, and we can find that time that our maximum occurs. So that maximum occurs at 328 milliseconds. We take that 328 milliseconds, plug it back into our voltage equation, and we can solve for that maximum voltage. So we solve here that at 328 milliseconds here, or 0.328, since this is in seconds, 0.328, we have our maximum at 48.9 volts. 48.9 volts. So we're able to graph that. And the other thing we might want to know is how long does it take for it to settle out? What we looked at before was in terms of time constants. It takes 5 time constants for an RL or RC circuit to die out, to less than 1% of its final value. So if we can look at a settling time for the time it to drop to 1% of its maximum value of Tm. So how can we solve for that? Well, we know we solved for the maximum, so 10% of that maximum is going to be 0.489, and that's going to be equal to e to the negative Ts minus e to the negative 6 times Ts, and we want to solve then that for Ts. So we can divide out both sides by 84. We can't combine these two terms. If they're multiplied, we could combine them. It's not easy to combine these without using a solve function, but we can see that this is going to die out much more quickly. So if we just focus on our e to the negative Ts, we can take the natural log and say that's approximately equal to just negative Ts. So our Ts then is approximately equal to 5.15 seconds. And that's where that dies out to our 0.489 or 489 millivolts. In noting again that Ts and it's approximately equal to 5 tau 1, or tau 1 was equal to 1 second. It's a little bit greater than that because we were looking from time from our time of 328 milliseconds to begin with. So that's how we can solve for a circuit, an overdamped circuit, determine that it is overdamped, solve for the voltage equation, and then we can solve for the maximum voltage and the time for the maximum voltage and the settling time.